this video, we're going to talk about drawing valid conclusions, and we're going to start to answer the question, what is geometry all about? Take a look at the following example of a type of reasoning called inductive reasoning. The marble I pulled out of the bag was blue. The second and third marbles I pulled out of the bag were also blue. Therefore, all the marbles in the bag are blue. Is the conclusion drawn here valid? What do you think? You might be thinking, just because the second and third marbles that I pulled out of the bag were blue doesn't mean that the fourth and fifth marble also has to be blue. Maybe the fourth marble would be pink. Maybe the fifth marble would be yellow. Let's take a look at the next example and think about, is the conclusion drawn here valid? A student was trying to think of numbers that were divisible by both 4 and 10. The student knew that 8 and 16 were divisible by 4. The student also knew that 10 and 30 were divisible by 10. The student made the following conjecture. There are no numbers divisible by both 4 and 10. You might be thinking, well, I can think of some numbers that are divisible by both 4 and 10. How about 40? How about 80? How about 160? There's actually an infinite number of numbers that are divisible by both 4 and 10. This is another example of inductive reasoning, and we're beginning to see what the problem is with inductive reasoning. In the first example, inductive reasoning was used to help us draw the conclusion that all the marbles in the bag are blue. But all the marbles in the bag don't have to be blue. We don't know that for sure. We didn't see all the marbles in the bag. Over here, in this example, inductive reasoning helped us to draw a conclusion that actually wasn't true, that there were no numbers divisible by 4 and 10. Now that we see what the problem is with inductive reasoning, let's talk about what it is. So inductive reasoning is when you make generalizations from specific observations. Take the marble example. We started with the specific observations that the first, second, and third marbles drawn from the bag were blue. And from those specific observations, we drew the general conclusion that all the marbles in the bag had to be blue. In other words, inductive reasoning is when you draw conclusions from patterns that you see. Conclusions that are drawn from inductive reasoning are called conjectures. And as we saw, sometimes the conjectures drawn with inductive reasoning are not always valid. Sometimes the conclusions are not valid. That's why in geometry, we really like to use a type of reasoning called deductive reasoning. Here's an example of a type of reasoning called deductive reasoning, and then afterwards we'll talk about what it is. All men are mortal. Harold is a man. Therefore, I can conclude that Harold is mortal. Is this conclusion valid? You might be thinking, yes, it is valid. If it's true that Harold is a man, and we know that all men are mortal, then it logically follows that Harold must also be mortal. Deductive reasoning is when we draw conclusions based on facts, rules, and logic. We can use deductive reasoning to prove that a conclusion is always true in every circumstance. In geometry, especially when we get to proving statements, deductive reasoning is used often. We have information that we start with, given true statements, and we use our postulates and theorems to draw conclusions with logic and reasoning. Remember, a postulate is something that we accept without proof, like a rule, and a theorem is something that we can prove, and once we prove it, we know it's true all the time, and we can use that as a fact as well. So once again, when we start proving things in geometry, we mainly use deductive reasoning. We start with given true statements, and we combine that given true information with postulates and theorems that we have in order to draw valid conclusions and logically reach our conclusion that we're trying to arrive at. Let's practice drawing some valid conclusions. So based on the diagram in part 1, let's think about some valid conclusions that we can draw. You might be thinking, well, T is the midpoint of points A and M of line segment AM because T is in the middle. That might cause you to say, well, since T is the midpoint, it's bisecting line segment AM. It's splitting it into 2 equal parts, where AT is congruent to MT. Although that's really tempting to say, diagrams are often deceiving in geometry, and they're never drawn to scale. So we never want to trust diagrams based on how they look. They don't tell us that T is the midpoint in this question. And these congruence marks on each half of AM weren't there to begin with. We put them there. We assumed that. In geometry, we don't want to believe anything based on assumptions. Anything that we say, we want to make sure that we have a reason to draw that conclusion, that the conclusion is valid based on what we actually know. So let's think about some conclusions that we can draw just based on what we know for sure. Well, I know T is for sure between A and M. I don't know if it's exactly in the middle of points A and M, but I know it's definitely in between them. I also know that points A, T, and M are collinear. Notice how they are all on the same line. I can also say that if I take AT and I combine it with TM, AT combined with TM makes the whole line segment AM. That's the partition postulate. So here we have a couple of conclusions. There's also other ones. We can say that we have line AM here. We can say that we have some rays. I'll name one. We have ray TA starting at T going in the A direction. We have line segments, a bunch of conclusions that we can draw that we know for sure. Moving on. Number 2, let's think about what conclusions here we know for absolute sure that we can draw for and know are true just based on what we have here. So, based on what we have here, I can see that we have some supplementary angles. CHL and CHN is an example. If I take this angle and put them together, I get a straight angle. So I'm going to write that here. Angle CHL and angle CHN are supplementary. Not only are they supplementary, but they also share a vertex and a side in common. They're connected or attached to each other. Do you remember our name for angles that are connected or attached to each other, right next to each other, sharing a vertex and a side in common? If you were thinking adjacent, then you are absolutely correct. And remember, we have a special word for angles that are both supplementary and adjacent. We say that they form a linear pair. So I'm going to write that here. Angle CHL and angle CHN form a linear pair. And once again, all that means is that they are both supplementary and adjacent. That's all it means for two angles to form a linear pair. There's other linear pairs in this diagram, but I think we get the idea. Let's take a look at the given over here. We're given that E is the midpoint of line segment BD. So this time, we actually know E is in the middle. So we can draw the conclusion that BE is congruent to ED. And I'll write my justification down here. A midpoint splits a line segment into two congruent parts. Let's take a look at B. Think about if you remember the word for the relationship between angle 6 and angle 5. I'm going to write here angle 6 and angle 5 form a linear pair. And I'll put my justification down here. Angles that are both supplementary and adjacent form a linear pair. Let's take a look at the given and the conclusion that we're trying to reach, and then we'll figure out how to explain why the conclusion is valid. We're given the angle KLP, so that's over here marked with the two congruence marks, is congruent to angle KNP. That's this angle here. And we're also told that angle PLN, so over here, is congruent to angle PNL. Our goal is to show that angle KLN is congruent to angle KNL. Let's think about why that is true. If we take the angle in purple over here, that's angle KLP, and we combine it together with the red angle, that's angle PLN, putting them both together makes the whole angle KLN that we are interested in. And over here, if we start with the purple angle, KNP, and to KNP, if we combine it or add it to this red angle, which is PNL, what we get is this whole big black angle, KNL, that we were interested in. So what we used here to combine the smaller angles to get the bigger angles is called the addition postulate of congruence. And we use the addition postulate when we have given information that is smaller than what we want to end up with. So we need to combine the parts together to make the whole thing, to make something bigger. In order for the addition postulate to work, we do need to verify that we're starting with two congruent angles. We do know that KLP and KNP are congruent because that was given. And to each of these two starting congruent angles, we do need to be adding on two congruent angles for this to be true. We do know that PLN and PNL are congruent because that was given to us as well. To go from our addition to what the addition actually is, let's think about what postulate we're using. We're saying the purple and the red angle together is actually this. And the purple and the red angle together is actually this. So we're just replacing the addition with what it is actually, with something that's equivalent to it. When we replace something with something else that means the same thing, that's the substitution postulate. So we explained in symbols. I know at the top it said words. If I was explaining this in words, I would say I need to put the parts of the angles together to make the whole big angles. And since we're starting with two congruent angles and adding on two congruent angles to each one, we end up with two congruent angles at the end. But I think it's easier to see in symbols. Another one, and I believe this is our last slide. Nope, one more after that. That's okay. So we are given that MP is congruent to NQ, and we need to arrive at the conclusion that MN is congruent to PQ. Let's think for a second. We're starting with MP, and we need MN. Is MN bigger or smaller than MP? You might be thinking smaller. It is. So we're starting with something that's bigger, and we need to get to something that's smaller. NQ, what we're starting with, is also bigger than PQ, what we need to end up with. So we need to take our given information that's too big and make it smaller. So it looks like we're going to be using the subtraction postulate of congruence here. Let's think about what we can subtract to get the segments that we want to end up with. So I know that we're starting with MP over here. What could we take away from MP to be left over with just MN? It looks like if we cross off the green part, NP, from MP, we're just left over with MN. Oops. We took off NP. And that left us over with MN. Okay, let me erase so we can talk about NQ. So we're starting also with NQ. And we need to figure out what we're going to take away from NQ to get PQ. Here's NQ. We need PQ. It looks like we're also going to be taking away the green part to be left over with PQ. And that leaves us over with PQ. So we use the subtraction postulate of congruence. So remember, to use addition or subtraction, you have to be starting with two congruent things. And we do know MP and NQ are congruent because that was given. And from each of those two congruent things, we need to make sure what we're subtracting is also congruent. Is NP congruent to NP? It seems like the answer would be yes, but it's not given to us. So we actually need to write that down. And we need to put a justification for that. Remember, the postulate that says that anything is congruent to itself is called the reflexive postulate. So we do need to justify that NP is congruent to itself before we can be subtracting it and ending up with congruent segments. MP, take away the green part, is MN. NQ, take away the green part, is PQ. Do you remember the postulate that can be used to replace the subtraction with what it actually is, to replace something with something that's equivalent? If you're thinking the substitution postulate, then you would be 100% correct. Once again, we explained in symbols, but if we wanted to explain in words, I would say we started off with segments that were bigger than the segments we wanted to prove are congruent. So what we did is we took the larger segments that were congruent And from each of those segments, we subtracted NP, which was congruent to itself by the reflexive postulate. Since we started with two congruent segments, and from each of those we subtracted two congruent segments, we ended up with two congruent segments, MN and PQ. But once again, I do think it's easier to see with the symbols. Two more examples. So in number 1 over here, we're given that angle ABC, so that's the whole angle, is congruent to angle DCB, so that's the whole angle. And we're also given that angle X is congruent to angle Y. The conclusion that we need to reach is that angle A is congruent to angle B. So I'm already seeing that the angles that were given, the green angle, is bigger than the angle that we want to prove are congruent. So we're given the big angles and part of the angle. So it looks like to get the other part of the angle, we're going to have to do some subtracting here. So let's think about what we're going to subtract. When we subtract, like when we do like 10 minus 4, 12 minus 6, we always start with the bigger thing so that we don't end up negative. So I'm going to start with the big angle here, angle ABC. And if we take away angle X, we're left over with angle A, which is what we wanted. Over here, we're starting with the big angle DCB. And if we take away angle Y from angle DCB, we're left over with angle B. Which is the angle that we're interested in. Once again, the step over here was the subtraction postulate of congruence. In order for it to work, we have to be starting with two congruent segments. We do know angle ABC and angle DCB are congruent because that was given to us. And we need to be subtracting two congruent segments. And we do know that angle X and angle Y were congruent because once again, that was given to us. The green, take away the blue, was the yellow. The green, take away the blue, was the yellow. Do you remember what postulate can be used to replace the subtraction with what it actually is, what it's equivalent to? If you were thinking the substitution postulate, then you are absolutely correct. Let's take a look at the next one. Here we're given that AB is congruent to CD, and we're given that BC is congruent to itself. Do you remember what postulate justifies something being congruent to itself? If you were thinking the reflexive postulate, then you are definitely correct. That's the postulate that justifies something being congruent to itself. But here it was given to us, which is nice. And the conclusion that we need to reach is that AC is congruent to DB. AC is bigger than AB and BC. DB is bigger, longer than DC and BC. So since we want to draw a conclusion about segments that are bigger than the information that we started with, it looks like we're going to have to put some pieces together or combine them, and that sounds a lot like the addition postulate to make things bigger. Let's talk about what we're going to be adding. So let's start with this side. We have information about segment AB. Let's think about what we can put onto AB to make AC. If you were thinking BC, that sounds just about right to me. AB, adding on BC to it, gives us AC, which is what we want. Let's go onto the other side now. We're starting with information about DC, or CD you can call it, but I'll call it DC, so we're going this way. We have to figure out what we're going to put onto DC to end up with DB. Let me get a different color. I start with DC, and I add on CB, which is also BC. Same thing, same two letters. Now, this is how we end up with segment DB, which is what we want. Here we have our addition postulate of congruence. AB plus BC is AC. DC plus CB is DB. When we replace the addition with what it actually is, that is the substitution postulate. Let's just verify that our addition worked. AB and DC, our starting segments, are congruent. That was given. We marked it in our diagram as well. BC is congruent to BC. That's given to us. If it wasn't, we could have justified it using the reflexive postulate. So our addition works. We're starting with two congruent segments, and to each of those, we're adding on two congruent segments. How do you know when to use the following postulates? So I'm not going to write down the answer to each of these. You can feel free to write it down, but I will talk about it. The addition postulate of congruence, we use that when we have parts of a line segment or an angle, and we need to get a bigger segment or angle. We need to combine the parts into something bigger. To use the addition postulate, you do need to be starting with two congruent things, and each of the things that you're adding also has to be congruent to each other. So that way you end up with congruent things. Subtraction postulate of congruence is when you're given an angle, angles or segments that are larger than the conclusion that you're trying to reach. So you need to take some stuff away from them to make them smaller. Just like with addition, to use subtraction, you need to start with two congruent things, segments or angles, and from each of those two congruent things, the things that you're subtracting also need to be congruent to each other. And that way your difference is congruent. Substitution is when we replace something with something else that's equivalent or means the same thing. We just substitute something for something that's the same. Replace one thing for another, substitute one thing for something else. And the reflexive postulate says that anything is congruent to itself. For example, BC was congruent to BC because they were the same thing. Anything is congruent to itself. The last thing I wanted to mention, and it didn't come up in the questions, but I do want to mention it, is when we have perpendicular lines, and that's our symbol for perpendicular. Perpendicular lines form 90-degree angles. So I'm going to just draw two lines here, line A and line B. And I'm going to tell you that line A is perpendicular to line B. As soon as I see this symbol, in my mind, I think perpendicular, I think right angles are being formed. So I know that where lines A and B intersect, where they meet, they form right angles. And remember, our symbol for a 90-degree right angle is a little box. Just like when you have a right triangle, the little box indicates the right angle. Anytime you see the word perpendicular and you want to mark right angles in your diagram, put the little box to indicate that they're right angles.